So at this point in the course, we've talked about Newton's first law, we talked about Newton's second law, but of course Newton's got three laws, so it's time to introduce Newton's third law. Sort of the common way that we usually say it is that for each action there is an equal and opposite reaction. So the first thing to make sure is very clear is that action would have been Newton's way of saying force. So sort of the more modernized version of Newton's third law commonly would be that for each force there is an equal and opposite other force. So let's think about this simple situation here. So we've got a box of mass m, here's our box, rests on a horizontal surface, or the weight of the box, here's the weight pulling down, and the normal exerted on the box by the surface at Newton's third law pair. So the question is, do these two forces constitute this third law pair that Newton's talking about up here? So is one of these a force that the other one is an equal and opposite reaction to? So take a second, think about this, sort of pause the video for a second, think about it, come up with an answer. When you think you're ready to go, then we'll come back and keep moving on. All right, so to check your answer, the answer here is actually no. These two forces, they are equal in magnitude, they do point in opposite directions, but they don't constitute a Newton's third law pair because, again, this common phrasing of Newton's third law is missing some very important details. So the sort of more appropriate way to think of Newton's third law is this. For a force that object A exerts on object B, there is a force of the same type that has the same magnitude, equal, but points in opposite direction that object B exerts on object A. So we still have our equal and opposite, but what we've added are these additional details. And so one of the things that we can do is, if we want to be clear about labeling our forces, then an effective label to use would be, I have a force of a certain type on object A by object B. And the thing that's useful about this is the free body diagram I'm drawing. This has got to be the same for all the forces. So you'll notice that here I've drawn the free body diagram of the box. I've got the normal force exerted on, in this case I've labeled the box as mass 1, so on the box by the surface. And here's the weight, right, the gravitational force exerted on the box by big E's the Earth. So notice that this number's got to be the same for all of the forces if they're going to be in the same free body diagram. So that's one nice thing that this labeling helps us check. The other thing is it gives us a good sense of where I need to go look. So in what free body diagram do I need to go look to find the Newton's third law pair to each of these two forces? So the Newton's third law pair, so if I've got two forces that I want to think of as a third law pair, they have to satisfy the following criteria. Equal magnitude, opposite direction, right? For every action there's an equal and opposite reaction. Those are the two that we sort of always get. But the two that we often miss is it has to be the same type of force, and then I've got to switch which object feels the force and which object causes the force. So basically what this means is, in my notation, I need to switch the force on and the force by. So the force on is which object feels the force. The force by is which object's causing the force. So if I want to think about the free body diagram, or the Newton's third law pair for this gravitational force acting on the box, well, its Newton's third law pair needs to be a gravitational force. It's going to point up. It's going to be in the free body diagram of the Earth because, again, what I've done is instead of on the box exerted by the Earth, I want the gravitational force on the Earth exerted by the box. That's the Newton's third law pair. And you'll notice, same type of force, opposite direction. Switching my labels tells me where to go look. So this one's going to be in the free body diagram for the Earth. And then the force is going to be equal in magnitude. So it'll be a force that points up that's equal to the weight of the box. What if I wanted to look for the Newton's third law pair for this normal force? Well, again, where to go look is in the free body diagram of the surface. So I know it needs to be a normal force. Since this normal force points up, right, the surface pushes the box upward. Well, the box pushes down on the surface. So I know that Newton's third law pair will point down. I know it's going to be in the free body diagram of the surface. And I know that the Newton's third law pair will have the same magnitude as this normal force. But Newton's second law tells me that these two forces cancel each other out, which tells me that the normal force here has the same magnitude as the weight on the box. So I know that the normal force, this Newton's third law pair, how much the box pushes down on the surface, is equal in magnitude to how much the surface pushes up on the box, which Newton's second law tells me is equal in magnitude to the weight of the box. So this is actually putting together what I know about Newton's third law with what I learned from Newton's second law in thinking about this particular force. So that's the idea of these are the four criteria that two forces must satisfy if I want to think of them as Newton's third law pair. And we'll see what the important thing is about recognizing those Newton's third law pair when we start talking about collisions.